Hello everyone, I'm Chen Gong, and I come from the Chinese Academic Sciences Institute of Automation. Many thanks for watching this video. Today I'm going to talk about our work. The topic of my presentation is Cooperative Multi-Agent Reinforcement Learning with Hypergraph Convolutions. As you see in this topic, in this paper, we use the hypergraph convolution technology to help improve the cooperation between different agents in a multi-agent system. And this work will be published on ijcnn-22. First, I want to introduce what is a multi-agent system and why this problem is so important. In reality, there's so many scenarios we can use the multi-agent system, like the control traffic and autonomous driving and dispatching and games. So many real application problems can be modeled as a multi-agent system model. So there are many multi-agent reinforcement learning methods to solve this problem, like independent learning, communication, and the most important one is value decomposition method. A full cooperative multi-agent task can be modeled as a decentralized, partially observable Markov decision process, in which agent only takes a local observation of the environment. And typically, decentralized, partially observable Markov decision process can be defined by a tuple. You can see this. S is the global state of the environment, and each time step, each agent can choose an individual action, which is denoted as U, and P denotes the state transition function. All the agent is decentralized, partially observable Markov decision process shares the same global reward function. According to the observation function O, each agent can get a local individual partial observation Z, and the goal is to maximizing the discounted return. We can see this example. It's a football game, and the football game can also be regarded as a decentralized, partially observable Markov decision process. The team's goals can be regarded as a common reward for all players of the team, and each team member's field of the vision is limited. And the third one, I want to introduce the why and what is the value decomposition and why this method is so important. In the field of cooperative multi-agent reinforcement learning, it's not feasible to train each agent individually, or treat all agents as a whole or joint training when the number of agents is so large. Therefore, some researchers have proposed various methods between the above two extreme methods, such as the William Q-mix. And this value decomposition method tries to achieve automatic learning of decomposition of the joint value function based on the individually global maximizing. You can see this equation. As we mentioned above, in our paper, we use the Hypergraph technology to help improve the cooperations between different agents in a multi-agent system. And in this section, I will introduce how to use the hypergraph to do our goal and how to realize the improvement of the agent. We first see this example as we show in the middle figure. The hyper edge is epsilon 0 in the left part connect nodes B, C, D, and disconnect connects A and E. And the middle figure also presents that how neighborhood information on the hyper edge epsilon flows. And the right part shows a normal graph that equals to a hypergraph epsilon 0. And a hypergraph G is consisted of a vertex set V, and N represents the number of the vertices, and edge is E with M hyperedges. In this section, we can know how to indicate a hypergraph using the hyperedges. And then we can use the hypergraph evolution to represent the cooperations between different agents. And the hypergraph convolutions ijcn is divided as this, and P denotes the weight matrix between the Lth and Lth plus 1 layer. Then I want to introduce how to build a hypergraph. We can see this example. A nano function is utilized, which takes individual observation z as the input, and it generates a real value vector ai, where m denotes the number of the hyperedges. And then we can use the ReLU operation and make the negative weights to change to the 0. Why we should do this? Because negative weights break the IgM equation, and also negative weights make the hypergraph invisible. And then, inspired by the GCN, we add an n-dimensional identity matrix, which is denoted as H2, and n is the number of agents. So, as we introduced, we can describe the cooperation or the information between different agents using the hypergraph technology. And then in this section, I will introduce our experimental environments, SMSC. And we evaluated the performance of our algorithm in StarCraft 2. And we used the StarCraft 2 multi-agent challenge environment as our environmental platform. SMAC is based on the popular real-time strategy game StarCraft 2, and it is a well-known experimental environment for the decentralized partial observation Markov decision process problems. It contains a series of scenarios, and each agent in SMAC can only observe partial state information and shelf reward function. Though the performance of multi-agent system in these different scenarios, the decision-making ability of the multi-agent in a complex problem can be evaluated. Last but not least, in the last section, I will introduce our experimental result to show that our proposed method can improve the learning efficiency of the multi-agent systems. The first is the main body of our experimental result. We can show that our proposed method, ijcnn-mix, can achieve a high performance than the SOTA method we compared, and we can see in this figure and this picture. In both the 12 scenario environment, our proposed method both achieve a higher performance than the SOTA. And the second part of our experimental result is the ablation study. We can see this picture. The first picture is a winning rate for different number of hyperedges. And the second picture is the winning rate. We only use the one-hot matrix. Compared with these two pictures, we can say that using the help agents can improve the performance of our method further. The last part is additional experiments. From this picture, we found that there are only 4 or 5 helper agents learn different connections in MM2. This result shows that only 4 or 5 essential connections exist between agents in MM2. Now, when the number of the help agents is greater than 4, and our method achieves a similar level of the performance with a different number of the help agents. And in this paper, we proposed a novel method using Hypergraph technology to help improve the cooperation between different agents and to improve the performance of the multi-agent algorithms. And we hope we use this paper to caution more people in this community to focus on or pay more attention to use the cooperations technology to enhance the cooperations between agents and to improve the performance of the multi-agent learning system. And many thanks for your listening. Did you have any question?